So good evening and welcome to the latest installment of the SLAC Public Lectures. So today we're very fortunate to have Quynh Nguyen, who is a staff scientist here at SLAC. Quynh did her undergraduate degree at Temple University, and then she went to Boulder, Colorado, the University of Colorado, to the laboratory GILA under the National Institute of Standards and Technology, which is like one of the world's great laser laboratories. And there she did some amazing stuff. And after that, in 2020, got her PhD, and she came out here to us. We think we're also one of the world's amazing laser laboratories, except that our laser is an X-ray laser. And so today she'll tell you about all kinds of incredible things that X-ray laser can do, and all the incredible things that the scientists have to do to make sense of what comes out of it. So Quynh, it's all yours. Thank you very much.
Great. Thank you, Michael, for the intro. Can you guys hear me okay on the back? Great. Yeah, thanks for being here today on a Thursday night where you can go out for dinner. I know some of my friends didn't make it because they're out for dinner together. So I am Quynh, as Michael introduced, and oh, I forgot the laser pointer. And today I'm very happy to tell you about what I've been working on in the past couple of years since I've been here at SLAC. And so hopefully at the end of this talk, you will learn something about what we do with supercomputers and what we use them for and how we use them to understand better. And in between that process, we make really good use of our X-ray light sources here. So before I get started, let me give a quick introduction about myself. I did my undergrad in chemistry and math at Temple, and I had an opportunity to do an internship at Lawrence Berkeley National Lab, and I saw the first synchrotron light source. It's one of these big light sources back in 2013. And then I took a gap year and went to Japan to work in an atomic physics lab where I saw my second synchrotron light source in Japan at the Institute for Molecular Science, and then moved to Oregon National Lab, which is another DOE lab, where I saw the third synchrotron light source. And then after that, I went to graduate school at GILA, and it's a joint research institute for precision measurement. So during my time there, people successfully measured an extra digit for the gravity constant, if you know what that is. So there's already a bunch of digits, and we got a few more. And it's a joint institute between University of Colorado Boulder and the National Institute of Standards and Technology. And then after I graduated, which was at the dawn of COVID, I moved here in 2021, and there was nobody. All the restaurants got shut down. I barely saw anyone. I saw my advisors for the first time outside of Zoom, and they look quite different from what I imagined. I didn't even say hi to one of them because I didn't recognize him, and he's right there. And then since I've been here, I've worked in many different places. So most of my postdoc work was done at DAISY in Germany. So I traveled there a lot, lived there for a long time, commissioned a new setup, and then it just got shipped here to SLAC, and we're going to install it on our new free electron laser. And then during that time, I worked at many different light sources around the world. So there are 5 different free electron laser, big ones around the world, and I've been to all of them, which is really, really nice. So let me tell you what we do here, or what these so special light sources do. So they have this unique capability that allows you to look into very tiny little objects. And you can find these tiny objects in pretty much almost anything that you see. In the chair, in the table, at the core of the earth, in materials, in your phone, or in proteins. You can find them anywhere. And because we have such a unique tool that allows you to look at these tiny things in the fundamental processes, we can touch upon all kinds of different science topics and not just one. So today I will focus on materials, since it's what I've been working on in the past couple of years. Before this, I was looking into what's happening inside the core of the Earth, and I figured out how to make it in the laboratory and study it in the laboratory. So what do we use materials for? So a lot of you may have seen a wafer, which is this circular big thing that you can hold it. And I have a number of friends who work at big semiconductor companies who they all hang one of these in their house, which I'm pretty sure is illegal because they took it out of their company, but it looks very cool. And if you zoom in to one of these wafers, you see these tiny little chips or transistors, and they're very, very small. So these allows you to gate or amplify electronic signals or powers. And if you look inside a central processing unit or a CPU in your classical computer, there are billions of these in each of those. So the way that I would describe this material is that it's a three-dimensional block. So there's not much flexibility that you can make changes to it. But what we want to do is we want to design the next material that's the best for transferring information and technology. So we have to find some ways to do that. What we can do is imagine if you peel off layers and layers from this material, like playing Legos. Then now you have a bunch of pieces that you can put them together however you would like. You can make a fox or a fountain, anything that you can think of. Or you can stack them together in a stack and make it a 3D object. But now imagine going to a restaurant where you have a menu and you can pick out which appetizer that you want, which entree. You can do the same thing here. You can pick out your favorite materials, your most favorite properties, put them together, and turn the device into what you want it to be. So this sounds great, but why do we want to do that? Now, if you take a closer look, you see a bunch of atoms or balls, and around these atoms, there are electrons. Electrons and atoms or ions, they move together. So if you move one thing, the other thing will eventually follow. So if you want to control how electrons move, which is how we control how information flow, then if you move the atoms, the electron will move with it. So now, if we stack these materials in different configuration, either in a staircase pattern or different symmetry, you can control how electrons flow in a different way. And that's what we want to do. And we want to have electrons flow very, very fast. So here I show a few examples of how you can do that. It sounds wonderful that you can design your own thing and it can do what you want, but it's actually not easy. Because once you put these things together, how do the electrons actually flow and how do the atoms talk to each other? So it takes a lot of calculations and a lot of computers to calculate the properties. And then you sit there and wonder, did my calculations make sense? Did I predict something that makes any sense? So someone has to go and make it in the lab, where it takes a whole process where I've never made anything in the lab, but it takes a whole process where you grow, you have a big substrate, and then you grow something on it, you lift it off, move it around, and make sure it's clean. And it takes quite a long time. And to make high quality material, the process costs a lot. So you cannot make that many high quality devices all at once. And then it comes to, how do you know what you're making? Is it usable? So somebody has to characterize it and look inside to see what is actually inside the device. Then this process is also a challenge because you have to look at it so carefully that now you're acquiring a huge amount of data, terabytes, petabyte size of data. And it takes a long time to go through these data. So up until this point, there's a lot of humans involved looking at these data and using classical computers that takes months or years. But it's really difficult to make progress if you do something and then you get feedback a year or 2 years later. But luckily, there are solutions. So we've been hearing a lot about artificial intelligence. So the question is, what do they do? Here, there are ongoing partnerships between private industries and DOE National Laboratory or Department of Energy National Laboratory, when we try to solve these big questions. So here are a few examples. The first one is a partnership between Pacific Northwest National Laboratory with Microsoft and Micron to visualize and calculate these properties very, very fast. So as soon as you think of something that you think you want to make, you can visualize using the tool that they're making. And follow this effort, Google DeepMind in London and Lawrence Berkeley National Lab have a joint AI robot that makes 400,000 new materials every day. And I should mention that the first collaboration for material prediction predicts 2 million new materials every day. So the question is, how do you know that the materials being predicted are usable or even can exist in the world? Because there are a lot of things that just cannot exist due to stability and all kinds of reasons. But that's what we can do here. We can look inside these materials, learn what the new properties are, feed back to the theory, and say whether or not you're correct. And that way we allow them to train the theory model or train the AI. And we can do it very quickly because we've developed this tool that allows us to do thousands of tasks all at once by distributing the tasks among supercomputers. And we do it jointly with NVIDIA here and with the Linac Coherent Light Source where I work. So today I will focus on the last part where we talk about how we make these things happen. But before I go into what we actually do, let me briefly go through why we need X-ray. And if you've been to a previous talk, I hope, I'm sure you've seen something like this, where if you want to take a picture of something, the light that comes out of the camera needs to have the wavelength that's equivalent to the size of that object. So if you want to take a picture of a bee, then the light from the camera the wavelength of the light have to match the size of the bee. So if any of you have been to one of these CuPyNumeric particle physics family day or family events here at SLAC, we have this laser diffraction experiment where I am one of the designers. But we use a laser, diffract off of your hair, and then you can use the diffraction pattern to back calculate the width of your hair. And we have family members with 3 generations come in, and everybody did the same thing. And we saw that the hair width decreases with the age of the family member, which I thought was really cool. I don't know if it's good news or not. But, so what we care about is we want to look at very tiny little things. So if we look inside of materials, what you can find or what you will find are a bunch of molecules like this, where they're sticking together through something where we call chemical bonds. And we want to see what happens when we poke one of those atoms. And I'll tell you why in a little bit. So here at SLAC, luckily we have all of the tools that give you all kinds of different wavelengths. So in other words, we have different sizes of cameras that allows you to take pictures of different things. But I will focus primarily on this region here where we have a bunch of molecules and a bunch of atoms. So how fast do you think they move given how small they are? So let's take a look at the timescales. So I'm sure you're familiar with horses. They move on the order of seconds. And given the same amount of energy, if the object is small, is smaller, then it moves faster. If you look at the hummingbird, their wings flap very quickly, and they flap on the order of milliseconds. If you pay attention to their wing flapping, your eyes cannot resolve the motion of the wing. And if you look into even smaller things like protein foldings, that happens 1,000 times faster because now they're just getting smaller and smaller. Now, how fast does an atom or a molecule move? They are even smaller than protein foldings. So every time I take a step, it's 1,000 times faster. So by the time we get to atoms, it's 10 to the minus 15 seconds. So we cannot resolve it by eyes. But what we can do is to use X-ray to take pictures of how fast they move. And then that gives us insight on what's happening. So why do I care about one single atom so much when it's so tiny and who knows if it's going to make any impact or not? So in a material or something like this, if I replace one of those atoms and put something else in it, it will change the property of the material. So what you can do here is, it's a similar principle on building a quantum computer. I'm sure you've been hearing this a lot, and how we have new quantum computers nowadays. So if I plug out one of those atoms and put something in, I can make it a qubit. And if I do that to several atoms, then I make an array of qubits. What happens is they can talk to each other and transfer information. And the promise is the information gets transferred a lot faster than a classical computer. They're not working that way just yet, but that's the promise. So we want to understand how to make them behave the way they want, the way we want them to, which is transferring information very fast with very little error. So yeah, so I just described the one of the applications here, or some other applications that we can use these materials for is you can stack them together and have electron transport from one side to another and increase the electron transport by having multiple layers on top of each other. So it's the same concept like quantum computers, or the way I like to think about it, instead of putting everything on one computer to run, now you put it on 1,000 computers to do everything in parallel. So it's a very similar concept in my head. And this is a model of what we can do or what we can make for a quantum chip. And it's a tiny little chip if you've seen one of these quantum computers. And they all look kind of similar if you've seen them, except for the chip that's on the bottom of this huge thing. That's the difference to how people make their qubits. All right, so what do we have here that allows us to look at these tiny little things? We have all 3 different types of light sources. The first one is the smallest one, so they do come in size. A tabletop laser that allows you to make these wavelengths for extreme UV lights. They're used to be about the size of the podium there. Now they're getting smaller and smaller, and they're very compact and very stable. But here at SLAC, what I use primarily for my work are the synchrotron and the FEL. And they're slightly different because they have different time duration. So the FEL can see faster moving things than the synchrotron, and they have different nuances. So in case you wonder if you have seen the X-ray free electron laser before, I'm pretty sure you have, if you have been on the plane at some point. Oh. So when you take a fly back into SFO, 30 minutes away from landing, if you look out the window, you have a window seat. Then you see this really long thing running underneath I-280. And it only took me 4 years working here to realize that that's the case, because I never look out the window. And this thing is about 3 kilometers long. And you can see different sections are being labeled because we have multiple accelerators along that or more than 3 kilometers long. And these different accelerators allow you to look at different kinds of problems because of the way we look at, the way we try to understand these problems. We look into the fundamental mechanism that's inside. So let me go into detail a little bit on how this works, or let's do a virtual tour walking down the accelerator. So we first have bunches of electrons, and this is a different directorate called the accelerator directorate. And then they send these bunches of electrons. I'm not qualified to talk about them because I work, oh, I do have a job. Okay, thanks. I pressed the wrong button. So I'm not qualified to talk about these, but I am qualified to talk about the other side, which is the photon size, where you can go from electrons, deliver to the photon size, and send to different experimental hutches. And we have a lot of them. Each of them have a different color theme and sort of different mascot or animals theme, something like that. And inside of each of these hutches, there are different types of instruments that allows you to measure different aspects of a material. So we look at everything using multidimensional techniques to really understand what's going on and confirm what we're doing and what we're seeing that is correct. And we can do it for pretty much all of these systems here that you can see. So now, what do I use them for? So here, coming back to this same material again, and if I use these different wavelengths, I can control how the electron move and how to excite them. So I can put in this much amount of energy, excite them just a little bit and see what happens. It's like you use your phone and it gets really hot. I can resemble the situation in the material and see how it responds. That's how we develop better materials for computers and devices. Or I can use one of these X-ray and excite the material to really high and completely rip them off of the atoms. So you can choose whichever topic that you want to use that fits your scientific question. And then what happens is we use an ultra-fast laser to excite the electron, and the X-ray acts as a camera that takes images of what's going on. Or we can also use the X-ray to excite the electrons and use another X-ray to take images of what's going on, or vice versa. So you can tune these around depending on what the question is. So let me take you through the accelerator. So first we go through the undulator, which is the crossing between the electrons and the photon size. And then you go into one of these experimental hutches, where this is our area manager, Ariel, and Ariel is making sure everything, all the cables are plugged in, everything's gonna work. But it's not just Ariel, it's a whole team of scientists and engineers. And some of them are sitting over there to make sure that we have an experiment and they run smoothly and continue to develop new technologies that open up answers to scientific questions. And then all of these different cables and motors, when we turn on the X-ray or the laser, we all have to be outside of the hutch. So we control everything from something from across the hall, where we call the control room. And it's a room of 10, 15 TV monitors. So if you watch one of these NASA movies where they launch a rocket, it's sort of the same room. Well, that's how I felt when I first walked in. And this hutch, spirit animal is a python. So you can see a python lying there. And then, why do I call it a hutch and not a lab? Because it's really, really big, like the size of a basketball court, or probably bigger. For those of you who are familiar, I'm using pictures of many different hutches here just to give you different views of the laboratory. So now, where does the X-ray go and where does the X-ray come from? You always see a straight line of some sort, and the X-ray always travel through that straight line. So now back to that hutch. So here, when you go into a hutch, there's always a straight steel tube. That's where the X-ray is traveling. And you send the X-ray all the way from the undulator to the experimental site or the experimental setup. So make a note of the big green hanging thing there. It's a robot arm where we hang our detector. And you can move this detector around using the robot arm to catch the signal. And this is a picture of the experimental setup. You may notice the quality and the resolution because all of these photos are professionally taken. And I took this one during an experiment at like midnight or something. So the X-ray is coming all the way down to that chamber over there. And so when I say X-ray, it also means photons. So photon comes in, interact with a material, and then photons come out. And when they come out, they carry some information about the materials. And we can extract the information from those photons by catching them. So here in this chamber right here, let me zoom in and tell you what's inside the chamber. So inside the chamber, there's a big silver parabola thing where there's a hole in the center and the X-ray goes straight through that hole. The laser comes in from 90 degrees on the side, hit the parabola and reflects to the same point as the X-ray because that's where the sample is. And now scatter photon comes out and we catch the scatter photons from outside the chamber. So what happens here is you can tune the arrival time of the laser and the X-ray to catch the motion or make a movie of what's happening. Because the laser comes in, excite the electron, and the X-ray comes in at the same time, it watches what happened to the electron. Then you can start taking snapshots of what happens to see how the electrons relax to equilibrium or back to the normal state. Okay, so how do you get to do one of these experiments? It's kind of expensive. It costs about probably close to $1 million. And for 60 hours beam time, if you get chosen for the proposals. So first, someone has to submit a proposal. So it's primarily universities, different institutions around the world, and they put in a proposal. From the time of proposal submission to do the experiment, approximately is 1 year. And this 1 year timeline includes you get accepted, discussion with the scientists and the engineers here to figure out the best way to put together a setup or to develop even new technology to answer the scientific questions being proposed in one of these proposals. So that process usually takes a year. And then from the experiment start, which is step 1, where assuming you have all of your setup tested and everything works well, then you can collect data. And from the data, you can then you start having this huge amount of data that you're collecting. So you have to process and analyze it, and it takes a long time. And then so what we can do or have been doing up until this point is doing preliminary analysis of the data where you look at a small, tiny amount of what you're actually collecting. And then from there, you extract understanding that allow you to make decisions and keep steering the experiment. And the decision making and data analysis requires a lot of people. So this is just, I think, 1/5 of the people that we had at the beam time. And those are there are some students and scientists driving the beamline, and the students are continuously doing data analysis to keep up with the acquisition. And step 1 to 3 has to happen within 60 hours. You have this precious 60 hours that costs $1 million, and better not lose it. So make the most out of it. And then after this 60 hours, people go back to their research lab or go back to their life and try to write up new scientific findings. And this typically it's a multi-year process because it involves surfing through hundreds of terabytes of data, cleaning them up, doing analysis, trying to understand the science behind, doing theoretical calculations, and that end up taking a long time. And the cycle repeats where now they have new results and they can continue to submit the proposal. So I keep saying that the data is huge. So let me tell you why it's so big. So we have this detector, if you recall the robot arm that moves around to catch signals. You basically can put it anywhere to catch signal coming out. And hanging on this robot arm is a detector called Jungfrau. So it's made in Switzerland at the Porsche Institute. And every time they make a new detector, they name it after a mountain. And they do the same thing with their experimental setups. So Jungfrau is one of the mountains in Switzerland. And this detector here, what I'm showing here is this 5,000 pixels. And when you change the timing between the laser and the X-ray, you can make snapshots of movies of what's going on, how the atoms are moving, how the electrons are moving. And now you can put it together. So that's one dimension of the data. And then within the detector itself, the intensity of the photons or the scattered photons is another dimension. And across the detector is what we call the momentum space. So we have this tiny little material. We have signals coming out at all angles, and we catch this whole range. And at this range, we call it a momentum space because those of you who know, it's a Fourier transform of the real space. If it doesn't make sense, that's fine. So how much is terabytes of data? So imagine if you wake up every day, take 4,000 pictures every day. That's how much a terabyte or a petabyte of data is. Or if you put flash drives of gigabytes next to each other, it takes about 92 football fields in size. So this is a Stanford football stadium if you've been. So it's a lot of data. And now we're in terabyte regimes with LCLS-I. With the new LCLS-II that we had just commissioned last year, it will be petabyte size. So the question is, how do we go through these and extract meaningful information out of them in a realistic timeline? Because remember, I mentioned that currently it's already taking multi-years. Now you have 1,000 times more data. I'm just not sure if we're going to be publishing at all. So let's take a closer look inside one of these data sets. I promise, I only have one slide on this. And so you see a bunch of signals. Each of those, what we call diffraction peaks. And they represent the orientation of the atoms. So if you rearrange the atoms, you will see different sets of peaks. So what we want to do here is to change the properties of the material using temperature. So we cool them all the way down to minus 42 Fahrenheit. So remember, the freezing temperature is 32 Fahrenheit. So we put them under very, very cold temperature. What happens is the atoms orient themselves into different positions. And the way that we know that is to do this diffraction experiment where you see different sets of peaks appear. And that's what you're seeing. And the traces in the middle panel corresponds to the movement of these atoms, which direction they're moving and how they're moving with respect to each other. So here are the cartoons on the right tell you the possible motions that the atoms can have. And believe it or not, we can tune how they move by the way we let them interact with the laser. So you can have the laser come in at different angles. They might move differently, or have the laser come in a different polarization or different configuration. They will move differently. So we do have a lot of control over their motions. The question is, how do we see what we're doing? That's a very difficult part. So what I'm showing is a very optimistic situation where you have huge signals and you kind of know where they are. But for some experiments, this is what you see, or a lot of experiments, this is what you see. So it's a detector screen of a whole lot of nothing. And after you spent months calculating where you expect your signal, and now you're sitting in this 60 hours beam time, and you see an empty screen of detector, it's very disappointing. So what we end up doing is acquire data for a long time and cross our fingers, and then have 5 different graduate students and postdocs drawing boxes around the detector to find the signal. It's extremely painful because I was one of them. So what I came up with is, how about instead of sacrificing 5 grad students doing that, we have an automatic tool that does this for us, everything all at once. So I worked with our collaborator here, NVIDIA, and we developed this new tool that's very cool. So instead of looking at one region on the detector sequentially, now I look at the entire detector all at once. But instead of doing this on one single computer, I do this on many computers. And this many computers is what we call a supercomputer. So DOE has multiple supercomputer sites. So what we do is we send the data to these supercomputer sites, and we do the analysis there. So we luckily also have access to NVIDIA internal computer with all the new chips. So we've been testing on both the NVIDIA computer and the DOE computer. And what I'm showing here is the signal analysis of one of those small regions that I used to have to draw by hand. So what you're seeing is the signal, the region where there's a lot of signal. So now, if you recall from the previous slide, there are a bunch of oscillations that tells you how the atoms are moving. So what I want to do is I want to find signals like this. So what the tool does, what the code does is it looks at the whole detector. It tells me where the signal doesn't exist, and then it can throw that data away, and we don't have to save it. When it does see signal, what it does is it applies a fit to it and extract the oscillation information. And it also tells me that there is signal. And it works really well for the 1% signal that we have to sit around and find for a long time. So now you might wonder, do they perform the same way or do they perform at the same speed? Turns out they don't, because every supercomputer is slightly different. So, and the difference is how you configure the chips or how you put them together. So in this case, the NVIDIA one, unsurprisingly, have better chips, so they run faster. And they're about 1.5 times faster than the current DOE supercomputer. And by doing what I just described on these two computers, what we end up with is a 172x speedup, meaning the process that used to take us 15 hours, now it takes us less than 5 minutes. So instead of taking, so what I didn't mention before was for the 60 hours, it's divided into typically 5 shifts, and each shift is 12 hours. So if the analysis of one scan that takes 10 minutes requires 15 hours, so you already don't get the feedback during the experiments. What you can do is only look at a small section of the data that doesn't give you a complete picture. Now with the 5 minutes analysis, we can get feedback instantly. So what we have demonstrated here is, so it's the same cycle before, if you recall, during a beam time. But what we have improved is the live analysis feedback of the entire data. So we get a full picture of what's going on, and it allows us to make smart decisions on what we want to collect or what we want to acquire during the beam time. And it makes us effectively use the time that we have. And what it also does is it helps a lot with the data processing or analysis after the beam time. So a lot of these multi-year time goes into surfing through these massive amount of data. So a lot of my time at Stanford here is surfing through data. If you're looking to go to Stanford for grad school or something, keep that in mind. And decide to do X-ray stuff. So I spent a lot of time going through data. So now these tools help a lot because instead of spending months or years, now I can spend weeks or days. So it's huge. So what I just described to you is this tool that applies to not just material, it applies to all kinds of science because of the way we look at things. We look at tiny little things or atoms, and we see how atoms interact with each other and what happens when you replace one atom with another. How does this new atom or this new friend, it's like you're going to school and then there's a new kid and they have to get along with everybody. So how does this new atom communicate with the rest of the atoms? Does it make the material better or does it make it worse? That's what we want to know. So this tool now can apply to all of these science categories that I just described. And hopefully it will be useful and people will make good use of it. So with that, I want to acknowledge or thank you everybody who's been working on this, specifically for the exascale computing side. We have our wonderful friends here at NVIDIA, and keep in mind, and also our members at SLAC, and keep in mind that's a much bigger team who we talk to and get advice from. And I want to thank the funding agencies and the SLAC Public Lecture Committee for inviting me and for making me practice for the talk. And on the experimental data side that I showed, it's a lot of people and it's a multi-international project. So each of these beam time requires 20, 30 people, or at least for this one that I'm showing here. So I just wanted to show their affiliations and all the groups that made the experiment possible. With that, thanks everybody for being here and listening to me.
Okay, now we have some time for questions. We're recording this session, so we'd like you to do the following. Please raise your hand and be recognized. There'll be microphone runners in 2 aisles. Oh, please, on that side. Ah, you're there. Okay. And so wait until you get the microphone and then speak into the microphone. And then you can be heard throughout the auditorium and also in Zoom land and also for the people who watch this later. So please, any questions to Quynh? Yes, please.
Hello, great talk. I was wondering about the data transfer, like to the supercomputers. Where is the NVIDIA center and where is the DOE center? And does it take a long time to transfer the data and how is it done?
Yeah, so that's a really good question. So we're getting there. So the DOE center is at Berkeley, so it's just across the bay. NVIDIA is in Santa Clara, so it's right there. And so we have colleagues who just developed a new streaming method that allows us to transfer data much faster. So we are going to try that. So I don't have the rate yet in mind because we still have to do testing. But hopefully it's not days or just in seconds. But also keep in mind before we send the data, we compress them first so they become smaller.
Thank you. A good presentation. I'm specifically interested in the model on how you took this sea of data that you're trying to parse. Were you using neural nets to try and discern stuff, or how did you train the model to look for interesting events?
Yeah, so I would distinguish between machine learning or artificial intelligence from high performance computing. So what we've done here is basically using the NumPy code that I wrote, or the Python code that I wrote, and then we expanded it to the full detector, and there we just do straight scaling on GPUs. So we scale up to hundreds of GPUs. Yeah. So there's no training just yet.
Right. So it's algorithmic that the engineers or the scientists are actually programming
Yeah.
the GPUs directly, and then you just iterate it across many GPUs.
So it's more than that, because so this infrastructure was not in existence before we started the project. So what happens is, along the way, we had to develop functions and APIs that worked for GPUs. And then the program, what it does is, this platform called Vision, what it does is it decides how to distribute the tasks very effectively, as opposed to the conventional multi-GPU code. You have to tell it how to distribute the tasks. That's the difference.
All right, thank you.
Yeah.
Well, that was awesome and fascinating. Thank you. And since it's a public lecture, I'm part of the public, so I won't ask an advanced scientific question. But I'm just curious, like, what inspired you to do this, to dream of this, to be a scientist? What do you love about it? Like, how did you end up here doing this awesome work?
Oh, thanks for the question. I think it's serendipity, because I got an offer by a professor from the business school to cover all of the tuition in undergrad and give me a full ride. And then I will go into actuarial science and work for a company. And then the day that we're supposed to meet, he wasn't in his office. And I got an offer from another place for a fellowship to do scientific research. And I had to sign it that day. So I think, I don't know if it was by choice.
Or is it still by choice?
Yeah. And then I think, I guess what I like the most about it is the people. So it's really hard work and really long hours. And I have to travel a lot. And it may sound wonderful to people, but if you travel 10 times a year, it's very disruptive. But I think what's exciting is I get to interact with different people and learn a lot from them. And different people in different countries have different culture, but it's very important to find the people who you like to work with, and I was very lucky to have found them.
You said you were looking at the entire data at once using the supercomputers. Do you look at the data separately on the NVIDIA supercomputer and on the DOE supercomputer, or can you run them? You split the data and then are able to look at more data at once using both supercomputers?
Yeah. So we're developing the tool. So a lot of what we're doing is benchmarking on the capabilities of different supercomputers. So we run the exact same test on both. So what I've shown here is we were able to look at the full data on the NVIDIA computer, but on the DOE, we were only able to run half of the data. We just successfully scaled up to full data today by one of the team members. I didn't do it today. And so these supercomputers, they don't work the same way, because both hardware and software, if you structure them differently, then they behave differently. So they have their own issues that one would have to fix in order to get the highest performance.
Hi, thank you for your talk. I was just curious how the partnership between NVIDIA and SLAC came about.
I was volunteering at the observatory at Stanford. And then I talked to this person next to me, and it was Seshu, who happened to be a staff engineer who's working on some GPU parallel computing code. And I said, oh, why don't we try to parallel my code, or work on my code and develop a platform for scientific computing? And that's how it all got started. And then we started this partnership, and I go over to NVIDIA, describe my vision, and luckily they like it. And also Mike here likes it. He's the director of LCLS. And I think we have really good support to pursue this project.
Thanks a lot. A very nice presentation. I wanted to ask if the algorithm is open source, or if there is any plan to make it open source so that other institutes can profit.
Yeah,
of
so
it.
the cuPyNumeric itself is an open source. The code to do this particular thing is not yet because we're there. So I want to do an end-to-end model, and we have not yet reached the end-to-end. But eventually it will be open to the whole user community when it's ready.
Yeah, I think almost all software written here is open to the whole research community. Maybe,
Not all of them.
sorry?
Not all of them.
Well, big projects like this.
Yeah, so eventually it will be when it's ready.
And we'll have the next of these public lectures, I believe, at the end of May. So please, if you're subscribed to our mailing list, watch for the announcement. If you're not subscribed to our mailing list, well, you can go to the SLAC website, look under public lectures, and put your name in there, and we'll give you announcements of all of these. So we hope to see you again soon, and we'll have some other aspect of the amazing things that we do here. Thank you all very much for coming.
Thanks, everybody.